Hi everyone, Parker Glynn-Adey here with Math 223. We're going to look at activity 1 from week 11. So it says, explain why a set of two non-parallel vectors in R3 is linearly independent. Okay, so to get started on this, I just want to recall the definition of being linearly dependent. Okay, so linearly dependent means that there's some kind of dependency among v and w. So what we're going to have is two non-zero constants such that these add up to the zero vector, right? So we can get a linear combination of non-zero constants that adds up to the zero vector. Okay. So let's suppose that we've got two non-parallel vectors. And that these are non-parallel and dependent. Okay, so if we're non-parallel and dependent, we get a relationship like this. Okay, so what we can do is we can take this relationship and say that they add up to 0. This will then give us that one vector can be stretched to obtain the other vector, right? We can say AV is negative BW. Okay, so assume that A is the non-zero one, right? One of these two numbers has to be non-zero. So we're gonna assume that it's A. Okay, so then we can rearrange. We can get V is negative BA times W, and that means that V and W are in the same direction. Okay, and if we have that these guys are in the same direction, right, that one can be obtained from the other by scaling, then they are parallel. Okay, which contradicts our assumption that they are non-parallel. Okay, so what have we got? We've got if they are dependent, then they are parallel. Okay, which is exactly what we were trying to show. That non-parallel implies independent. Okay, I just want to sort of draw a picture of what's going on here to sort of clarify geometrically what's happening. Okay, so we've got our two vectors. There's V. There's W. And if these are pointing in different directions, right, then they be linearly dependent. An interesting point about this proof is that we didn't need to use R3, right? That this actually holds in any dimension. Right? So this argument about parallel and non-parallel works in any dimension, which is kind of interesting. Okay, so just wanted to point that out as a bit of an aside. Okay, excellent. So we'll move on to the second exercise. If you've got any questions about this, please ask on Piazza. Okay, explain why two non-parallel vectors in R3 span a plane. Right, so first we want to understand what the span is. Right, so the span is the set of all linear combinations of V and W. And if we want to be a little bit more formal and write that out mathematically, that's going to be AV plus BW for constants A and B. So there's our span as a set. So what we want to do is we want to describe this set as a plane somehow. Okay, so we're going to find a normal vector to V and W. Okay, in order to find the plane, we're going to create a normal vector for it, and a normal vector must be orthogonal to everything in the plane. So let n be V cross W. So this is the cross product of V and W. Okay, this has the property that its inner product with V and its inner product with W is 0. Right, so this is orthogonal to both of those things. Okay, so now what I want to do is I want to show this normal is perpendicular to everything in the span. Okay, so what we'll do is we'll pick a vector in the span, and we'll show that it's orthogonal. Right, so we'll take our normal, dot it against AV plus BW, and get n dot AV plus n dot BW. Right, and that'll be A times 0, B times 0, which will all 0 out. Okay, so this normal is perpendicular to every element of the plane. Okay, excellent. So this sort of describes why these two vectors span a plane. Okay, and just to look at that visually or geometrically, right, we'll have our vectors again. W and v. Okay, and now when we take this cross product, we get a normal vector, which is going to be at right angles to both of those guys. Okay, this normal vector should really sort of be pointing out of the plane of the whiteboard. Okay, so this is pointing up at us away from v and w, and it's describing the span of the whole plane. Okay, excellent. Again, if you've got any questions about this, please check in on Piazza. We'd be happy to answer your questions there. What does it mean geometrically for two vectors to be linearly dependent or independent? Right, so we want to sort of get a handle on what this condition means geometrically. Okay, so for two vectors, we have this really nice theorem. That these guys, if they're dependent, that's equivalent to v and w are parallel. Okay, so if our two vectors are independent, then the picture looks something like this. Right, this is the picture for independent vectors, and the picture for dependent vectors looks something like this. Okay, just a bit of an observation that I want to make here on the side, that what's really going on here is a fact about dimension. Right, so notice that the dimension of the span of two vectors is either 1 or 2. Okay, so if span is one-dimensional, then the vectors are parallel or dependent. Okay. If the span is two-dimensional, then the vectors are independent. Okay. This will come up later on in the activity, but I think it's an important point to make now, that there's really a connection between number of vectors and the dimension of this span. Okay, so let's move on to the next part of the activity. Now we're going to look at what happens with three vectors. And the three-vector situation is a little bit more subtle than the two-vector situation. So I'm going to answer the second part of the question first. Are any two of them parallel? So to answer this question, what I have to do is I have to look at the vectors and say, can I obtain one as a multiple of the other? Right, I look at these guys and I say, there's no way that any multiple of this first one will give me a 0, or there's no way that a multiple of this 0 will give me a 1. Okay, so I can identify those two vectors as non-parallel. Same thing with the second and third vector. Right, no amount of stretching this 0 will turn it into this 1. There's no way that I can stretch this guy to obtain this guy. Okay. Similar arguments tell me that these guys are also non-parallel. Okay, so we obtain that every pair of vectors is non-parallel. There's no way to stretch any one of these three to obtain any other of the three. Okay, but now let's go back to the question of linearly independent. All right, let's look at whether these vectors could be linearly independent. Okay, so what we're going to do is we're going to try and find a relation between these three vectors. Okay, so to do that, we're going to look at them and say, can I add up copies of these guys to obtain this guy? And with a little bit of staring, we can see that this is possible. Right, we notice that if we take our second vector and add that, we get the following thing. Now that's equivalent to the following. Now this says that our third vector lives in the span of our first two vectors. Okay, so let's just make a note of that. That's going to become relevant for us in a moment. I also want to rewrite this as a linear span that adds up to 0. Right? Our usual format for linear dependence is that we have to add up to 0. Okay, so notice now we've got a linear combination of these three vectors. Okay, this linear combination adds up to 0, and it has non-zero coefficients. Right? Okay. Okay, so these non-zero coefficients tell us that we have a linear dependence among the vectors. Okay, cool. So are they linearly independent? No. Vectors are not linearly independent. they are linearly dependent. Okay, very good. So what that means, this third vector lives in the span of the first two. It lives in the plane defined by the first two vectors. So we'll move on to the next part of the exercise. For three vectors to be linearly independent, is it enough to check whether no two vectors are parallel? Okay. So as we saw, all of these guys are non-parallel. All right. And they are linearly dependent. Okay, so what that's suggesting to us is that it is not enough to check non-parallelness. Okay. We must also check that no vector lives in the span of any two vectors. Okay, so we must check that no vector can be written as a linear combination of the other vectors. Okay, so let's have a look at the last exercise. What does it mean geometrically for three vectors to be linearly independent? Right, so if we've got three vectors here, U, V, and W, right? If these are living in a three-dimensional space, then what we're asking is that each of the planes spanned by any pair of vectors are distinct. Okay. I encourage you to take your right hand and just look at your thumb, index, and middle finger. So spread those out into sort of the X, Y, and Z directions. This will help you get a grasp for what this is asking geometrically. Okay, this is a slightly stronger condition than what we had in the two vector case. In the two vector case, just as a reminder, I'll put it up on the slide. Right, for two vectors, independent is equivalent to non-parallel. For three vectors, this isn't quite true. We need the planes spanned by any two vectors are distinct. Okay, excellent. Well, that wraps up activity 1. I wish you the best of luck. If any questions come up, please ask on Piazza. Thanks for your time.